Hello and welcome to LLM Explained. I am your host and your friend Sambhav Dikshit, your fellow AI researcher and eager open source enthusiast. And today we are going to be walking through this beautiful paper on low rank adapter with gradient approximation, also which I'll abbreviate as LoRa-GA for the entirety of this video. So for those of you who are new here or are not familiar with the concepts of LoRa, I would recommend you to check out some basic beginner friendly LoRa videos first on how LoRa works and operates. You'll probably find that on YouTube, where the creator of LoRa himself has uploaded a basic tutorial on how LoRa works out. But if you have some idea of the concepts, this video should work just fine. And even if not, I'll give you a brief overview of how what LoRa is and how it works, so that you're still on par and up to the hood on how things would work out here. Um, Anyways, so let's start about what this paper is all about. So in this video, basically we'll be doing a careful technical walkthrough of LoRa-GA, and this is a very practical paper about making LoRa, which is one of the most popular parameter efficient fine tuning techniques, much faster and much more reliable by simply changing how we initialize those low rank adapter matrices. I'll explain why this matters, what the authors changed, and why this change is both conceptually neat and practically significant. So, let's start with the basic motivation. Fine tuning large pre trained models is essential, whether you're doing instruction tuning, RLHF, or adapter models to narrow downstream tasks. But full fine tuning gets prohibitively expensive as models scale. There's more compute, more memory, more storage, everything explodes. So that's why PEFT methods or parameter efficient fine tuning methods really matter. They let us adapt the massive models by changing far fewer parameters. LoRa is one of the mainstream PEFT methods. Instead of updating a huge dense weight matrix W, LoRa adds a low rank product B times A, so that the effective layer is so that the effective layer output Y is basically the huge dense matrix W plus some scaling factor eta plus B, the product of the low rank product B and A, and that multiplied with the input segments X. So I think even this paper does give you a brief through that, and we'll look through that later. Mm, Somewhere over here, that's about right. But we'll go over that. Anyways, so there's a but on a very rough scale, there is a very underappreciated and yet very important problem that vanilla LoRa often ends up facing. And the core problem that LoRa has is that empirically the community has observed that LoRa can require several times more training iterations and flops to reach the same kind of validation performance that it means that it would attain on full fine tuning. So basically the cheap method can become the more expensive one in terms of wall clocks and the flops, in terms of the flops that it takes, uh, sometimes even performing worse at the end. Even the authors here tend out to note that LoRa required 5 to 6 times more iterations and flops for the same performance as fine tuning under the same learning rate. And they've shown this in figure 1. So I feel like that's a good indicative of what problem vanilla LoRa faces. And I feel like this is what the motivation here is from the author's end, to explain and justify the need for a different LoRa method, particularly catering to how LoRa is initialized in the first place, so that a better initialization would give you a better output on the whole. um, as this is kind of the problem that they've tackled here. Moving on, they've discussed that this primarily for them raises the question as to why LoRa converges slowly, and their hypothesis is pretty crisp that LoRa's default random initialization. By the way, LoRa initializes itself is that B, the two matrices A and B, B is initialized to 0, whereas in matrix A has a chiming initialization to it. So the authors here are basically proposing that the initial directions of the adapter, if the initial directions of the adapter gradients don't actually align with the weight update directions of that the full model would take, the low rank adapter would have to discover these through training, which is what is actually causing, yeah, or costing the iterations here in the model itself. So the paper explores a simple idea that's very elegant, that if we initialize the low rank factors so that their first step gradient update aligns with the first step of the full weight matrix, then the subsequent updates will become better, approximate of the full fine tuning, and the convergence should ideally accelerate. The notion or the notation that they would ideally expect to claim is that the delta of the low rank adapter products B and A should be similar to the delta of the larger weight matrix W. I think they explore this somewhere along the lines here. So uh, let's see if we left out something here. I feel like the authors also emphasize on the importance of fine tuning on different advanced techniques like instruction tuning, reinforcement learning from human feedback, so on and so forth, as well as why PEFT is important. Moving on, they've discussed how LoRa works, and LoRa usually represents its output, the modified layer outputs, as y equals to w plus eta times ba in x, where eta is the scaling factor. And eta here is taken as alpha by r. The reason it's taken this way is because eta tends to keep proper scales while keeping the final predictional output rank agnostic. Again, this is some math that we can discuss out later, but roughly speaking, since B and A have a factor scaling factor of rank r, therefore eta being proportional of 1 by r tends to balance out the term factor for rank and keeps the entire thing rank agnostic. But we'll discuss this out in terms of mathematical factors later on. In terms of benefits, the authors also note that there's an empirical evidence for LoRa's slow convergence, 5 to 6 times lesser iterations, and they explore the cause of this, propose the hypothesis for how LoRa's initialization might be a cause for the slow convergence. And moving on, they propose a novel initialization method, which is something we've not discussed upon yet, so that the delta of VA is similar to delta of W for some positive constant C. I feel like that is a fairly well bit of an alignment on where they want to take this. uh, this is basically what they're proposing for their new method. So if we look at the figure here, instead of initializing B for 0 and A for chiming initialization, as well as eta as alpha by r for the that is for the vanilla LoRa, they are proposing to do this using SVD style decomposition on the gradient that initializes the adapter matrices on the top of the gradient eigenvectors. So basically, the adapters would be chosen in such a way that the adapters are aligned to the dominant direction of the gradient and not the weight, so that the adapter's initial gradient points in the same way the weights gradients would point out. Uh, This is what they've highlighted through the mathematics here in the initialization part of things as well. And a different scaling factor, of course, which is inversely proportional to 1 by root of r instead of 1 by r. Another important mathematical caveat that we'll end up discussing as we move to the mathematical breakdown of this paper. But again, this does ensure that the entire thing stays rank agnostic. So the full method also includes a stable ranking choice, and eventually, yeah, this does transition to numerical stability across the architectures and ranks. If we look at the results, which is something they've discussed in the abstract here, they've tested this on a subset of the glue dataset with T5 base, and LoRa-GA outperforms LoRa by an average of 5.69, which is an amazing performance considering LoRa itself is a widely used method. So any improvement on LoRa with making minimal changes to the underlying robust architecture that LoRa provides and has been trusted for so long is a win in itself. So I feel this paper on the very higher levels of it seems to highlight the fact that even smaller changes and simple and elegant changes to complex and well established methods such as LoRa itself can yield good results and faster convergence without having to change everything under the hood. The metrics speak for themselves, and different performance improvements have been highlighted throughout the paper, as you can see as a part of the abstract, with the improvements of 0.34, 11.52%, and 5.05 on the empty bench, GSM 8K, and human eval, respectively. Moreover, what's more exciting is that since the initial argument was for convergence, the authors here note that we observe up to 2 to 4 times the convergence speed improvement compared to vanilla LoRa, validating its effectiveness in accelerating convergence and enhancing the model performance. The code, as the authors note, is available on GitHub. I'll also drop a link for the same in the description below. But it's a beautifully well written and well maintained code. So for any of you who's eager to check it out, please do give it a look. It's really well written and well implemented code in the most optimal ways possible. So I feel like that's a very high level map uh, of what we are going to do here. In the rest of the video, I'll do three things. First, we'll step through the math on how gradient approximation objective is derived and implemented. Second, we'll examine the scaling and the variance stability details that make the initialization robust across the ranks. And third, we'll walk through the key experiments and ablations so you can see where the gains come from. I'll also highlight some practical considerations: how to sample gradients cheaply, how to often recompute, when initialization matters the most. If your maintainer or your researcher who's using LoRa very often, these are probably the precise places you'll want to understand. Yeah, I feel let's dive into the math next, real quick. We'll move over the related work section. For most part of this is related to how PEFT is and what different variants of LoRa are, and we'll dive into some quick math across, moving across the methods, looking into what how mathematics for vanilla LoRa works and how that's different from the gradient approximation methods that we're using here. All right. Now, moving on to the next section, we will understand the. We've already understood the motivation at a high level. Let's slow down everything and actually build LoRa-GA from scratch. So I'm going to assume that you've never seen, that you've actually seen a LoRa before, as I've said before, but I will not assume that you've ever carefully thought about why it converges slowly or what exactly is the low rank constraint to optimizing to or doing the optimization here. So we're going to rebuild the whole thing one step at a time. Before we write out any equations, and I'm sure there are plenty of equations in this mathematical section out here, as I can see from over the hood. Uh, Before we go on writing any equations, I would like to be very specific and very explicit about the problem that we're tackling here. We have a pre-trained model, a loss function, and we want to adapt the model to a downstream task. Now, ideally, the ideal thing to do here would be something like take a step in the direction that reduces the loss the most. That's it. Like everything else, PEFT, LoRa, adapters, the constraints that we impose on the behavior is basically leading to this ideal behavior. So the core question here becomes, if I cannot update all the parameters freely, how close can I get to the update that I wish to take? And that's a question that we should keep in our head, because everything that we do here on is basically an answer to the same. So let's start with a single linear layer. Let's isolate one layer, because if we don't understand what's happening in one layer, we don't really understand transformers as of yet. um, Let me take the whiteboard here. I'm not too proficient with this one, so bear with me for the same. But let's say if we're taking a single layer, we would have something like y. Let's say it would be somewhat of y is equals to uh sorry, this would be um we would have y is equals to uh, w times x. This is for a this is for a single linear layer. Wait, what? This is for a single linear layer. Cool. Now, think of this as one projection matrix in a transformer. Let's say a query or a value projection, and w is a big matrix, and x is the activation that's coming in. We freeze the pre-train weights. So let's be explicit about it, where we can just say that w naught is of the dimensions, let's say dimension out cross dimension in. So I would say that dimensions of w naught uh, would be, wait, w naught are basically some r of dimension out cross dimension in, right? These are the dimensions for the pre-trained weight matrix, and w naught is the pre-trained matrix. So I'll write this out as well. um, W naught is the pre-trained weight matrix. Pre-trained weight matrix, and this is basically what we get from pre-training. So let's be explicit and clear about this. We are not allowed to change it directly. Now, what would happen in a full fine tuning, right? So before LoRa or before PEFT, what would vanilla fine tuning, full fine tuning do here? So let me take that up. Let me say full fine tuning. Cool. Um, Now, ideally, the loss here, I'm not sure how to decrease the dimensions of this. Ideally, the loss here would be something of L of W, where the loss would depend on the weight. So basically I could say that delta of W of L, right? um so basically the loss depends on the on W, right? So if we were doing full fine tuning, we would compute the gradient of the loss with respect to every entry of W, right? And mathematically that would actually look somewhat saying like W1, it would look like W1 is equals to W naught minus ah, I'll have to use this, minus of alpha um delta W of L. I might as well just write this out entirety um, in marker. So I was saying um, W1 is would be equal to W naught minus of alpha of delta W of L. Right. Now this is basically the gold standard. This is the update direction. And in terms of what we see from the update directions here, it's pretty evident to say that the minus of delta WL, if I take this minus of delta WL, this would become the direction of the update direction. It is basically the best first order direction to reduce the loss, as you can see from this equation. If we could follow this direction exactly, the training would be maximally efficient. If I write this out, this will be the direction of the uh, uh, update, right? Yeah, this is the direction of the update. Now every PEFT method that we are seeing and that's being built out there is really answering just one question: how much of this update direction uh, can I approximate given my constraints here? uh, cool. So instead of doing a full fine tuning update, we could now introduce LoRa, which came into the equation so that we don't have to touch the entire weight matrix. All right. So with the LoRa into picture, let me write that out. LoRa, right? Because earlier we were discussing on what happens or what would happen in fine tuning. Oh, I didn't know you could click space and scroll. That's new for me. Um, with LoRa into picture, you can basically just start out by saying that or the way LoRa discusses this out is that instead of making a full matrix update, it says that hey, my weight update W would be W naught plus some delta W plus some delta W. And LoRa basically does not change the model structure. It only restricts the form to this delta W. And basically this delta W is essentially parameterized as eta, which is a scaling factor, times B times A, which are the low rank adapters that we've been discussing. Let me just write this as a mathematical equation as well. This is what delta W is essentially equal to. Cool. And here the rank of the matrix A is or the dimension of the matrix A is basically the rank cross dimension of input, and the dimension of matrix B is basically dimension of output cross the rank. So instead I'll write that out as well, um, where um, uh, dimension of A is equals to R cross dimension of input, and the dimension of B, the dimension of B is equals to dimension of the output cross rank. Cool. So instead of allowing this delta W to be to be any matrix, LoRa basically forces you to product it into two smaller, much skinnier matrices, A and B. This means that delta W has a at most maximum rank of R. So in a very critical juncture, you can see that LoRa is not just parameter reduction. LoRa is actually a rank constraint on the update direction. uh, Now, what does this constraint actually mean for us? So we can say that for the update that LoRa could provide, or let's say delta W, this essentially is belongs to all the matrices of all the matrices of a rank that are less than or equal to R. I'll write that down. All matrices of rank that are basically less than or equal to R. uh, and basically this shows that full fine tuning can move in any direction, where the full dimensions would ideally be the dimension of output cross the dimension of input, and LoRa can only move in low dimensional subspaces of that space. So in terms of optimization, uh, optimizing under LoRa is not necessarily about finding the best direction. It's about finding the best direction within that restricted subspace. Now, in terms of why this initialization here matters so much, um, I would say there's really something very subtle but important here. Since LoRa does not really restrict where we can move, it just restricts how quickly we can rotate that space. When we randomly initialize both these values A and B, uh, that means the column space of B and the row space of A, based on the dimensions of how they're initialized, are random. That would mean that the initial LoRa update direction is almost orthogonal to this delta WL, which is the direction of the update, minus delta WL, which is the direction of the update, or the or basically orthogonal to the true gradient, which is something you could call this. Let's also write that down. This is basically not the negative direction, that is the direction of the update, of course, but delta WL is basically the true gradient here. Um, so, in terms of how we would want this to go, we would like this to be so that something like delta of W LoRa, um, delta of W LoRa I might just write LoRa is LR for an abbreviation, since that would be much easier. And the true gradient um do would end up being orthogonal, so this would be close to zero here. So in early training, LoRa is not really descending. It's mostly just rotating the subspace to find the most useful directions out there, and that is why convergence is slow. Now we finally uh, have a goal that we can explicitly understand based on the problem that the mathematics presents here. If you could choose an A or a B very intelligently rather than initializing them randomly, like we do with LoRa, and it's not exactly random. As we've seen before, we initialize B to 0 and A to a calming initialization. But still, if you could initialize LoRa, the values, the low rank adapters A and B much more intelligently, what would you want them to do? And ideally, I would want this to have something like let's say, I would want this to have some sort of a way where the delta of W with LoRa and is very similar to the true gradient, the delta WL. Now this is what I would want out of my ideal LoRa initialization. My ideal LoRa initialization. Cool. So we want the first LoRa update direction to basically align as closely as possible with the full fine tuning gradient. Not exactly because of the rank constraint, but it could be as close to it as possible. And in fact, I might just say, since it's not exact, it might be with some constant c, uh, as we can see described here in this paper, for some non-zero positive constant c, of course. And that serves as the entire objective for LoRa here in the gist as well. So um, I think that is one part of things. Let us see. I think this is something I might have written. Let's remove that. Yep. So now we have the core idea of what we would expect out of our LoRa here. So let's reformat this problem a little bit. Let's actually rewrite this as a clean mathematical problem. Um, I should clean the slate, or let me just draw a line here, right? This is where we uh, reformat our problem. Is this right? Cool. This is what we've done so far. This is what we've discussed. And let's move to reformatting this a little bit. Let's rewrite this as a clean mathematical statement. Let me also add a heading here somewhere. Let's say re for. I want to zoom in a little bit. Um, yeah, let's reformatting the problem mathematically. Cool. So let's say there's a given matrix G, and we want to approximate it using an R rank R matrix, right? Mathematically, we could call that as uh, G is equals to delta of W times of L, and ideally uh, we would want that to be such that the minimum, sorry, of the um normalization. We'll go into Frobius normalization and things into detail later, but basically the minimum of the Frobius normalization of this matrix with its base rank matrix, where rank of M, where rank of capital M is less than equal to the required rank R. uh, this is what we would ideally want here. So now this is not like a deep learning problem anymore. It's more like a problem of classical linear algebra. So since linear algebra has already solved this problem for us, uh, we can take an SVD style decomposition here. So if we look at it this way, where I write it into two matrices, where I say G is equal to U times of, let's say, sigma V transpose, right? I think the paper might have discussed this as well. Let's also look at the paper so that we're not caught behind. Uh, yeah. So um, they want to this is what they've discussed throughout LoRa as well as vanilla LoRa, and initialization of LoRa. Oh, we did miss one thing. So basically LoRa, since we discussed, and I didn't say this out explicitly, but we discussed that the initial point of LoRa would ideally be want to be as close to the actual weight matrix, full rank weight matrix, as at the starting point. We would want that W dash would be equal to W naught, and this term be zero in the very starting. So since for vanilla LoRa, B is initialized to zero, therefore evidently for vanilla LoRa, the very first weight update, W is equals to W naught plus eta times of 0 times something else. So this term becomes 0 for vanilla LoRa and the first iteration. Let's write it this way. 0 in first iteration. So therefore W equals to W naught for first iteration, right? Now this is something that we would require even in LoRa-GA as well, and we'll see how that terms comes as a problem in terms of mathematical implementations. But for the time being, this is what happens in first iteration initialization in LoRa, or I should say vanilla LoRa. Now, please do note that for most practical purposes in this video, at least, when I am referring to LoRa, I'm referring to vanilla LoRa. So that should be pointed out here. Anyways, coming back to our problem at hand, let's say we break down G into like a SVD style decomposition, so or a truncated SVD. So when we look at it that way, if G is broken down or represented in this format, then you could also say that a matrix G with rank R could be a representative of UR into sigma R into VR of truncated. Uh, Sorry, transposed. This is not truncated. My bad. Sorry. Right. So the truncated SVD basically gives us the best possible rank R approximation for the gradient matrix in the Frobius normalization. This is how this has been proven by the Ernst Minsky Young theorem. I'm sorry if I'm mistaking the name here, but I'll drop a correction in the description or in the comments if I've mistaken the name. But the theorem basically ends up providing up with sufficient evidence to prove that this truncated SVT is the best possible rank R approximation for gradient matrix in Frobius normalization. There's no learning required, there's no heuristics. This is the optimal rank R decomposition approximation. So now if I was to connect this with LoRa, um, I could basically end up saying that B is equal to U times U of rank R and sigma of R by 1 by 2, and the comprehensive side of this would also imply that A would be sigma of R and product that with the transpose, since the dimensions actually verify this out. So this could be verified with the dimensional product as well, and this keeps the dimensions of the product of B and A consistent and coherent, indicating that this is also a valid choice. And basically this choice guarantees that B times A, if I do a B times A, it comes equal to U R times sigma R times V R transpose, which is where we set out to, which is also equal to G here, which is equal to G. So, which means that the LoRa update is already aligned with the dominant gradient directions. So, this does prove the mathematical theory part of it. However, this does bring a very practical concern, and a very natural question to address here is, if I'm not doing a full fine tuning, how do I actually get this G here? So, the paper here proposes that computing the gradient using small number of batches, either at initialization or in a in or accumulated over early steps. Now this is relatively cheap compute compared to the full training, since this only needs to be done once, and we need to focus on the fact that we are not training a full model here. We are only observing its first order behavior. So it's fairly practical for us to do this as a one time step, rather than doing a full training over and over again. And again, initialize doing this in a number of smaller batches at initialization, or accumulating this over early steps, does make it much more practical than going for a full fine tuning out there. Let's look at if we've actually missed out on any of this basic mathematics here. I think we've covered on vanilla LoRa, the gradient approximates, how vanilla LoRa manages to do the gradient approximates. Um, in terms of gradient descent with step this, assuming learning rate is small, we have an eta ba. We've also covered why we're using Frobius normalization, and the difference of these two updates as in criterion, which is something we've discussed over here, is minimum. Um, but and in terms of optimization behavior, uh, with LoRa-GA's initialization, the adapter subspace is aligned from step 1, and the early updates actually descend the loss. So I could see that there is no real time wasted in rotating across random subspaces. Therefore, LoRaGA does turn LoRa into first order approximation for full fine tuning, instead of constraining it to a low rank manifold. Um, in transition, I feel we've covered for most of the mathematical aspects here. Um, let's move on to the next section where we discuss the variance preserving scaling, or the scale stability. And then we can probably move to the initialization and the experiment section, and the practical implications of the same. Let's move on to the next section where we discuss the scale stability for the same. Cool. So far we've looked at initialization, as well as what the true gradient looks like, and a bunch of other things that describe the basic mathematics, as well as the direction of updates and basic mathematics for both LoRa-GA, how the initialization has been tackled, why it works out fine, what are the motivations behind it, how we actually came to being, and how we know that this is a better way of initializing as compared to vanilla LoRa. We computed its truncated SVD, we used it to initialize A and B, and honestly, it's at this point it's very tempting to think that great, problem solved. We'll just use SVD and we're done. But this is where many implementations quietly fail, because alignment is not enough. We also need to scale correctness. This is what this section is mostly about. So before touching equations, again, let's be very explicit about this. When we say scaling, we are asking how large is the contribution of the b times a times x relative to the w naught times x, which is the mathematical way we would have broken down if we looked at the equation. Y is equals to w naught plus b a times of x, assuming we didn't have a scaling factor here, which is what we are going to discuss here in this section. So more precisely, what is the variance that LoRa out of the LoRa output BAX, this one? um, if this variance is too large, then basically the training explodes, and if this is too small, then LoRa learns painfully slowly. So, and moreover, if this variance is dependent on rank, then the hyperparameters would stop transferring. So the goal is not just any arbitrary scaling. The goal is controlled invariant behavior. right? So let's now step into the mathematical side of it. um, let's break this equation down and say y is equal to w naught of x plus, uh, let's include a scaling factor for the time being, eta times of b a x. Cool. So this is the pre-trained output. This is the pre-trained output. Pre-trained output. And uh, this section is the LoRa contribution. Let me also write that down. I know the text is a little small. We'll make that bigger later. This is the LoRa contribution. LoRa contribution. Cool. And during early training, the behavior of the model is dominated by the relative magnitude of these two terms. What that essentially means is that if LoRa term, this one, is badly scaled, everything downstream breaks. The gradients, the activations, the optimizer behavior, everything breaks if this is not scaled properly. And let's look at how vanilla LoRa first handles this context, so that we are reminded of how it handles this problem. So let's say, so initially for vanilla LoRa, I would like to remind that the product B times A is 0, where, since because A is a chi-mean initialization, where it's basically between 0 and the variance squared, and B is equal to perfect 0. Therefore, B times of A is actually equal to 0. So, LoRa path contributes nothing in initialization. Nothing, absolutely nothing in the start, in the first training step. So, the training starts stably and the adapter grows slowly. So, that is why vanilla LoRa is stable but also slow. But on the flip side, as we've seen through our SVD initialization here for LoRa-GA, shame that we didn't write this is LoRa-GA. Uh, this is LoRa-GA. So we see that this, so here what is pretty evident is that B times A does not necessarily have to be 0, right? What that means is that this will not, while this will grow much faster, this will not have the same kind of stability that we get from vanilla LoRa, because its initial product is 0. And this is why scaling becomes more crucial here. It's not that scaling is not equally crucial for LoRa, because the subsequent training steps are also impacted by scaling, but LoRa-GA gets worsely impacted, much worsely impacted, since it is also initialized, since its initial step, or step 0, is also impacted by the scaling here. uh, let's see what goes wrong with native SVD initialization. So as we saw above, um B times, let's say, let's see how this thing differs for LoRa-GA. So for LoRa-GA, B is equal to UR sigma R half, of course, and A is equals to sigma r half, of course, V r transpose. What that transitions to is the equivalent SVD that we were seeing earlier. U r sigma r V r t, and this perfectly matches the direction gradient direction, but it really does not say anything about the the magnitude of the output. The singular values in sigma are really just depend on a couple of things. They could depend on the scale of the loss. Let's write that down. Scale of loss. They could depend on batch size. They depend on batch size. They could depend on uh, the task. They could depend on the layer. And what's actually worse is that the output magnitude actually changes with the rank, and this is a key problem here, because rank dependence for LoRa-GA would be a disaster, because let's say I run LoRa-GA with a rank 4 or a rank 16 or a rank 64. Then if the variance of B times A times X increases with the rank, uh, I would like to write this as well. So if variance increases with the rank, then the changing rank is silently affecting the learning rate, which would mean that let's just complete this. Then the uh, changing rank is affecting the learning rate. That would basically mean that the results here aren't comparable and the tuning isn't transferable. The Because the stability here depends completely on the rank, and this is largely unacceptable for a method to be practical. So what the authors here have done is imposed a very strong requirement. uh, so what they are saying is that the product B times A times X, uh, and that is squared, since the normalization we are using is Frobius normalization, should be invariant to R. This should be invariant to R. Invariant to R, as we've discussed so far, because being dependent on R would mean that the results, for the four reasons that we've described above, uh, would make it impractical or unacceptable as a method to use in fine tuning. Uh, so this is our central scaling requirement, that regardless of the rank, regardless of input dimensions or the layer size, the expected energy of the LoRa output should essentially stay controlled. which is what this variance preserving means here. Um, so let's now analyze the variance step by step to understand where this is going, and why the scaling factor that had been chosen by the authors was what it was. Um so let's say that x has zero mean. Let's take a couple of assumptions here. Going over this, uh, where was the yeah, let's pick up where we left off. So let's take a couple of assumptions, really simple and really sensible, standard, reasonable assumptions for internal activations. So let's say that x has zero mean, and the expectation of product of x and x transpose is an identity matrix. Then, using this, if we write the expectation for our low rank adaptation matrix outputs, uh, the expectation from this would transition to x transpose a transpose b transpose into b into a into x. If you're looking at the normal this part of this, um, if you use trace notation for the same, then it turns to this a transpose b transpose b into a, and this part becomes an expectation of x into x transpose if you pair these up. And since x into x transpose expectation is I, therefore this becomes trace of a transpose b transpose into b into a. uh, the variation of the LoRa output depends therefore completely on the Frobenius structure of B and A. So now if we look at this problem again, but mathematically, if we plug the raw SVD components, the trace becomes a function of the sum of the squared singular values and the number of retained components R. So, therefore, as R increases, the trace grows, the output variance grows, the training dynamic shifts, and this violates our requirement of it being incoherent to rank changes on the whole. What this would mean is that we would essentially have to fix the scaling here so that we are ensured that this is incoherent to rank in all senses. So the fix, or a simple solution, conceptual solution for a fix, would be to rescale both a and b so that the total energy of ba is fixed. And the way authors normalize choose to normalize this uh, is that we keep the direction that we get from the svd, but we renormalize the magnitude. So this is analogous to weight initialization schemes and variance preservation of fan in fan out logic that we usually see. But notably, this is not just cosmetic. The scaling is not just a minor detail, it's actually mathematical in nature, that it's key to the functionality itself, to the extent that this would end up defining a method that works with one rank versus a method that works with all ranks. So clearly this goes on to show that alignment determines where you move, but scaling determines how fast you move, and you do need both of them to move at the end of the day. Losing one or the other will only cost you your convergence or your loss, or both perhaps. So it's not a trade-off; it's a balance. That's how you look at it. If you zoom out of it and look at the larger picture here now, um, with variance preserving scaling, LoRaGA achieves three things. First is that the gradient aligned update directions stay stable. Second, the stable activation statistics are what you get. And third, you get a rank invariant behavior. So this, you can conclude that LoRaGA then becomes a very clever drop-in replacement for vanilla LoRa in all sets and perspectives, right? Um, but that I feel covers most part of scaling here. But apart from scaling, uh, we should now move to look into how experiments were conducted and how the authors aligned on fanning out experiments to verify the results on whether this actually performs or not, right? So let's look through the paper. There's a good section for experiments that is present here. um, let's go through this one by one. For starters, I can see that they've started testing out with the natural language and understanding, which is the NLU part. uh, so the first experiment that they've done is on a T5 that uses a T5 base on a subset of a glue benchmark. And this is like a decently controlled mid-scaled setting, since T5 base is large enough to show optimization issues, but small enough that full fine tuning is still decently feasible on the model. That makes it an ideal test bed to answer most basic questions. Does LoRa-GA actually improve the final performance compared to vanilla LoRa? What are the differences? And basic understanding on how natural language understanding tasks are handled by this new form of initialization. So uh, if we look at it, the authors are comparing the primary sets of comparison are full fine tuning LoRa-GA, along with a couple of other models like PISA, RS LoRa, LoRa Plus, Dora, Ada LoRa. What I am most inclined towards are the comparisons between full fine tuning LoRa and LoRa-GA. And what we observe here on the basis of the outputs is that vanilla LoRa achieves 82.08% average score. LoRa-GA achieves 87.77. And this is a roughly 5.5% improvement, which shows that LoRa-GA is very and which shows that LoRa-GA is actually very performing better than the vanilla LoRa, whereas it's also very close to full fine tuning. So the reason this matters is this is a very strong result, because on a standard benchmark with the same rank and the same parameter budget, simply changing initialization recovers most of the gap between LoRa and full fine tuning. And this establishes the core claim that LoRa's performance gap is not just about rank, it's also about where the training starts. Um, Moreover, once we move past this, we also see that the second thing that the authors would like to think on is how well the model converges. And based on the graphs that we see earlier and the claims of convergence, the authors have actually seen that even if the question arises, if the final performance accuracy improves, does LoRa actually converge faster? So they track this with validation performance versus training steps, basically flops versus vanilla LoRa and LoRa. And based on how the number of steps that the graph takes and the flops that it consumes, it's pretty well visible that vanilla LoRa require. They have observed that vanilla LoRa often takes 5 to 6 times more training iterations to reach the same performance as full fine tuning, and LoRa in many settings takes 2 to 4 times fewer steps to reach the same level of accuracy. So that has been like a decent improvement, and also a proof for the theoretical side to things, as to prove the primary hypothesis that a faster convergence is in order whenever there is a better initialization to the vanilla LoRa. um, Moving back to the order that the paper follows, um, we see that the next experiment that they've conducted is on large language models. which is a key aspect to experimentation and testing, since LoRa and other PEFT methods are primarily applied to large language models. So this is where you see most of their use case, most of their this is the regime where LoRa and their counterparts are primarily most heavily used. So in terms of how that goes around, they have actually the authors have actually decided to train this on three tasks: chat, math, and code. And we have benchmarks for all three of them. Let's look at them one by one. I feel like there's a table here. Oh, there's a table here. So let's start with empty bench. So empty bench is for instruction following evaluation benchmark. It broadly classif it's broad and a human evaluated benchmark. And on this benchmark, we see that LoRa improves over vanilla LoRa by, by a very small margin. And even though the gain here is modest, but that's okay. I mean, empty bench is a relatively high level task, and the gains here are generally incremental. So the key point that we see is, as long as LoRaGA does not hurt the performance, uh, and it still provides consistent improvement, I would count that as a win, and I feel like the authors would count that as a win as well. In terms of GSM 8K, one of the more important benchmarks here to note. This is a grade school math reasoning benchmark, and the task and this kind of task is like extremely sensitive to optimization quality. Keeping that in mind, LoRaGA improving in accuracy by almost 10-11% over vanilla LoRa um, goes on to show that the result actually supports the core idea of the paper, uh, that reasoning tasks depend heavily on since reasoning tasks depend heavily on this early gradient directions. If the model takes a wrong direction, it becomes ridiculously hard for the model to recover, which indicates that LoRaGA's gradient alignment not only matters, but is actually the ideal step that we would want to take for the model to actually uh, do a better initialization on the whole. Last, I see we have a human evals benchmark, which is a code generation benchmark. Uh, and usually there are not that huge differences in numbers here, because it's really hard to scale on code generation benchmarks. So even small optimizations can lead to large behavioral differences. That being said, I see there's like a almost 5% diff between LoRaGA and LoRa. So this is like a decently large code gain in as far as code benchmarks go. So this also supports the idea that better gradient aligned initialization actually goes on a long way in improving the fine tuning. Following this, the authors have done tests on rank sensitivity and stability, examining robustness of the model, and most of these results end up showing that vanilla LoRa can actually vary slightly based on how the rank is initialized, whereas LoRaGA is a little more stable with that regard. This proves the preserving scalability that we've talked about in the last section. They've also done rigorous tests on memory costs and runtime, and LoRaGA fared fairly well in regards to the same, indicating that this is also not too resource intensive as a model on the whole. So, conclusively, through these experiments, at least we can, in walking through these experiments in order, the story is pretty consistent. Taken together, the experiments show that LoRaGA is not a heuristic; it's a principled, scaled improvement on how low rank adaptation is properly done. And with that, I feel like we come to the conclusion of this paper on the whole. And over the course of this entire discussion, this entire video, I feel like we've started from a very simple observation that vanilla LoRa often converges slowly and performs full fine tuning and it actually underperforms full fine tuning in terms of convergence, even though it's supposed to be strong. Parameter efficient alternative is supposed to be that cost effective and cheap alternative, but it tends to underperform when comes to wall clocks and iterations. So what this paper shows is that the problem is not low rank adaptation itself. The problem is, instead of initializing LoRa adapters randomly, it aligns with the actual gradient direction that the full model actually wants to move in. And I feel like this single idea combined with careful variance preserving scaling changes a lot of things. And the mathematical implementation is sound. The math just sits right, the theory works out fine. And in terms of experiments, whether it be the T5 based experiments on with glue for NLU, or the convergence times, or experiments on llama on the empty bench, or GSM-K 8K, or human evals, uh, and other experiments as well, the overall results tie in together, and the theory, the intuition, and the empirical results all line up very clearly to indicate that LoRaga just works better, not just in terms of theory, but also on real world implementation. So on theoretical side of things and the conclusive side of things, this is what the paper says. But as a personal take, to talking directly to all the users and all the maintainers out there who already use LoRa today, or who are working with LoRa in some way or form, LoRaGA is not a rewrite. It's not an architecture. It's not a new optimizer. It's just a better default. You basically keep the same LoRa structure, the same training loop, the same parameter efficiency, and you just get faster convergence, better final performance, more predictable behavior. And for most of the people who are actually using this in their production grade systems, what becomes especially important is that LoRaGA reduces the sensitivity to initialization and rank choice, which means there are fewer sharp edges for the users, and fewer of those mystery failures that you get along initialization. On a more deeper level, this paper also sends a broader message, and it reminds us that PEFT is not just about saving parameters, it's about optimization geometry. Low rank methods don't just fail because they are low rank, they fail because they're misaligned. And LoRaGA shows that um, when you respect the gradient or the structure of the gradient from the very beginning, low rank adaptation can behave surprisingly close to fine tuning. So if there's one takeaway I want to leave you with, it's this: in large fine tuning, starting in the right direction usually matters more than we like to admit. This paper proves that in theory, in mathematics, as well as in experimentation. It's like a very clean and principled way of doing that. And it does it with a lot of simplicity, elegance, and beauty. For any of you who are inclined to look at this deeper, and I would really urge you to, you should definitely give this paper a read. As well as there is a beautiful GitHub repo out there that describes the actual implementation for LoRaGA, which has been implemented quite beautifully. So I would also encourage you to give this a look. Obviously, I'll drop the links for these in my description or the comments, however that goes. So feel free to check that out. And I feel that's enough on my part. Thanks for watching this video. If you're interested in maintaining or building any similar systems, or if you're writing such papers, or if you have any creative new papers that you want to discuss with me, or you just need somebody, or you're looking for looking to talk to some other ML enthusiasts, I feel free to connect with me. I'll drop my socials in the links as well. My Twitter handle is Sambhav Dikshit Pro. You can find me on LinkedIn and Twitter most of the time. And yeah, I think that's it for this video. We'll My GitHub is Sambhav Noob Coder, so if you want to follow me there, you can follow me there as well. But I think that does it for this video. Thank you all, and I hope we see each other soon in a next video with some new interesting research paper along the way. Till then, peace out, keep coding, keep building. Bye.